Hi there. Welcome to another video demonstration of the idun cartridge for the Commodore 128. So this is part two of my three-part series on programming with idun. Part one we did a C Hello World program targeting the Z80, and here in part two we're going to switch over to using 6502 assembly language and the Acme assembler, which is included with the idun cartridge. In case you didn't catch part one, I'll just quickly run the C program so you can see what its output is supposed to look like. So we'll do zload hello, and you'll see it just does some random position, random colored hello world text on the VDC display. And you press any key and it exits out back to the idun shell. So we're going to recreate this program now in assembly language. And we'll start by creating our file. So we use the Joe editor once again, and we'll do hello.asm will be our source code file. And so now we need to type in our Acme code. So if you've not used Acme before, it's a pretty handy, pretty powerful little assembler with macros and preprocessor directives. And so to start off, we're going to use some of those preprocessor directives. So the first thing I'm going to add in here is a to directive saying that we want the output of this ASM source code to be a binary called hello, and we want that to be in the plain binary format. We're also going to import some include files, and you do that with the source directive. So we need to import a file called sys/acehead.asm, and this is going to give us access to APIs. And we're also going to include some constants for the SID chip, because if you remember from part one, we need a random number generator, and we're going to end up using SID registers to get our random numbers. So that's file name is acme cbm c64/sid.asm. Okay, so following these directives, the next thing we need is some boilerplate code that you'll find at the top of any tool or program that's going to run within the idun cartridge. So we're going to have to define our base address or load address or initial program counter, whatever you want to call it. And we'll set that to the constant ace tool address. This comes out of that ace head file. And the first thing we want in our program is a jump to main. And the reason we want to jump to main is because we have some magic bytes that need to follow next. And we're going to have these 3 bytes called ace ID 1, ace ID 2, ace ID 3. And these just form a magic number string of bytes that the kernel can check for when it loads the file to see that, yeah, this looks like a legit file to run from the idun shell. And we also going to specify the stack size, and there's a reserve byte too that's not currently used. So stack size of 64 bytes for our program, and then a 0. So that's all the boilerplate you need. So now we're ready to start typing our actual code. We're going to need some variables. Again, if you remember the C program, we're going to need a counter. So before we did a loop of counting up to 200 iterations. And we're going to need a random number for the color. So we'll name that as such. And these are all byte size. And then we need a random number for the row, again byte size. And we're just going to define these as being 0-page registers. So 6502 0-page, very fast access. And you can use, with idun cartridge tools, you can have from position 0-page position 2 all the way up through 6F. Can be your personal 0-page variable space for your program. Again, we're going to need a message. So this time we do have a directive for PET format, so we don't have to worry about that conversion between ASCII in the source code and PETSCII in the output of the program. We can just define hello world the way we want as a PET string. And so that's the variables we need, and now we can go ahead and define our main. So we just set main equal to star, and that will be the beginning of our program. That's where it jumps to. All right, so what do we need here? Well, we said we're going to have a counter and it's going to go to 200, so let's set that up first. So we'll load the accumulator with a value of 200 decimal. Let's see if we can get some auto indent stuff going here. Auto indent on. And we're going to store that in the variable counter. And you can see, you know, for Acme we have nice source code highlighting once again here in Joe. So it's really pretty convenient, almost modernish type of editing environment, considering it's all running on a Commodore 128. But the next thing we're going to want to do is we're going to want to clear our screen. So clear the screen to black. And this is the VDC screen we're talking about. So how do we do that? Well, there's an API called asm+8502 CLS for clear screen on the window. So the currently active window that your tool is using as its console, we're going to clear that. And it requires some arguments, and the arguments are going to be in the accumulator. We have a value of C0, and that means we're going to adjust both the character and the attribute for all the cells for the whole window. So we load A with C0. We're going to load X with the character value. So we're going to use a hex 20, which is a space. And we're going to load Y with 0. That's the color. So color black. So black space is filling the whole screen, basically, color characters and attributes. So that will clear our screen. And the next thing we need to do is initiate our random number generator. So let's just put in a routine to be completed later called random. And that's all the setup we need. So now we can define our loop. And what are we going to do in our loop? Well, we want to check the state of counter, and we want to count it down. And while we're counting it down, we want to generate random numbers and draw in accordance with those random numbers. So very similar to the C program, but a bit more verbose than that 4-line for loop, because, well, it's assembly language. So it's supposed to be verbose and wonderfully unforgiving. That is the beauty of assembly language. So for a loop, we'll go ahead and load the counter into the accumulator. And if it's 0, we kind of want to jump out of the loop and quit the program, right? So we'll put a branch equal, which means the value is 0, to this placeholder called plus. So that's like a temporary label that you can use with Acme. You can use plus and minus as a label to jump either forward or backwards in your stream of instructions. So we're going to jump forward to the label called plus, and we're just going to do a return from subroutine there, which would actually exit our program and send us back to the idun shell. And we'll go ahead and put a comment, say exit to shell. Okay, and then within our loop, what do we need to do? Well, we're going to need to get our random numbers. So we'll have a routine called getRand, and we need to draw the text on the screen based on those random numbers. So we'll have another routine called draw, and that's all we actually need to do. Oh, and also decrement our counter. So it will count down from 200 to 0. And maybe we'll go ahead and put something in here to check to see if the stop key is pressed. So you could jump out of the program early. So check for stop. And we do that with another API. So this one is called ascon for console stop key. And if you're pressing the stop key, it will set the carry bit. And if you're not pressing it, it will remain clear. So we'll branch on carry clear back to loop. But if the carry is set, we'll actually fall through to return from subroutine, which is going to exit to the shell. So that's all we really need for our loop. Let's go ahead and save it just to be safe. So we'll press Control K and D, name a file to save. Let's take the default. So our file is saved and we can continue. So first function we need to implement here, or subroutine rather, is random. So let's define random. And what's random going to do? Well, random is going to take advantage of the fact that the SID chip has a noise generator. So just like most programmable sound generators from the 1980s, there's at least one channel for creating noise. And think of that as being useful for sound effects like explosions, or for like percussion instruments, where basically the underlying tonality, if you will, is just random noise. So the SID has a noise channel and that generates random numbers. So why not use that as a random number generator? And so to do that, we just need to set up the SID noise channel and start it running. And we'll use some of the constants that we pulled in from that source file above. And what we need to do is take a value of FF, and we're going to store that as the frequency high and low. So we're going to set basically the maximum frequency for our noise generator. So we'll store that value in SID voice 3, that's the noise channel, frequency low, and we'll also store it in SID voice 3 frequency high. And again, these are constants for the register addresses that come from that file we included above. And then we're going to load A with a different constant, this time the SID voice control register for noise. Whoops, not SOD, SID. So SID voice control noise, and we'll store that in SID voice 3 control. So we're setting up voice 3 to be our noise channel at maximum frequency. And that's all we need to do. Now we're going to be able to collect random numbers from the SID chip. So let's return from that. The next thing we need to do is define our getRand subroutine. So let's have getRand equals star. And we're going to need a place to store the raw random value that we get. So let's define random val as a variable here. And it's going to be a byte, and we'll initialize it to 0. So next up is our getRand function. What should that look like? Well, the first thing we need to do is just grab the number from the SID chip. So we'll do load A and SID voice 3 waveform output. That's our random number, and we'll store that into our variable random value. So if you remember from the C program, we want our color random value to be a value from 1 to 15, and we want our row random value to be 0 to 24. Or well, in this case, we want it to be just less than 25. 1 to 25 is fine because we're using a window, and the window has 25 rows. So for this instance of the program, we basically want 1 to 15 and 1 to 25 as our two random values. So we can take the value we already have and we can compare it to 15 to see if it's already in range. And if it is, we'll know that based on the carry flag. And so we can jump ahead. But if it's greater than 15, then we're going to need to subtract 15 from it until we get a value that's in range. So we'll have a little loop here where we subtract 15 from the accumulator, and then we compare it, the new value, to 15 again. And if the carry is set, then we continue looping. If not, we fall through. And so that's going to give us our 0 to 24, or 0 to 14 value. And then we just add an additional 1 to it. So we'll add back 1. And we're going to store that as our random color. So remember, we define this random color variable up above, and so we store that there. Now we need to do the same thing for the random row. So now we can take our initial value once again, so we'll load that value, random value, and this time we compare it with 25. And again, we're just going to loop while it's out of range. So we subtract 25, and then we compare it with 25. And on carry set, we're going to continue to loop. And otherwise, we're going to store that value in our random row. And return. But we're missing something up here. So after we do this first comparison, just like above, we need to branch on carry clear to the end of the routine. So yeah, so we have two little loops that check the value using 15 and using 25. And they should be identical. It looks like they're, yes, basically identical. Okay, and so now, finally, we come to the draw routine. It's going to actually put the text on the VDC display. So let's define draw. And let's first deal with the location that we're going to draw to. So that's going to be based on the random row. So let's load our random row value. And we also need an X value. If you remember previously, we used 2 times the Y value as the random X value. So we'll go ahead and create that X value by doing a arithmetic shift left. So that multiplies rand row by 2. And we'll transfer that from the A register to the X register. And then we'll reload random row. So now we have the X value in the X register and the row value, the Y value, in the accumulator. And with these X and Y values loaded into the X and A registers, we can call another API called asm+position, or pos, asm+pos. And this is going to actually get us the address in the VDC screen memory of that X and Y location. So it's telling us where in memory we're going to place our text. And that's stored into a syswork variable that we'll access with another API called asm+put. So ultimately what we want to do is take this location, return to us from asm+position, and eventually we're going to set up all the variables we need, and then we're going to jump to asm+put. And asm+put then will actually put that text on the screen in the intended location. So in order to set up everything, we need to tell it about the message that we're going to use. And we'll do that with the A and Y registers. So we're going to load A with the lower bytes of our message address, and we're going to load Y with the upper byte of our message address. So it's a 16-bit address for message, and there's the full 16 bits stored in A and Y in little endian order. And we're going to store those into some syswork variables. So it's going to go into syswork plus 2. And so store A syswork plus 2, and we're going to store Y in syswork plus 3. So we basically transferred that 16-bit pointer now to syswork plus 2 location for use by asm+put. Additionally, we're going to have to tell asm+put the size of our string. So that's going to be in the X register. And we're just going to load it with the size of our message. And we can get that by taking the address of message and subtracting the address of main. Because if you remember at the top, message was defined just before main. So a little computation there tells us the size. And we're going to store that into syswork plus 5. That's not right. We want to store X into syswork plus 5. And next thing we need to do is we need to load A and Y with 2 additional values that tell asm+put exactly what it's going to do here. So we're going to load A with a value of C0, and that's telling the API to update both the character data and the attribute data, because we want to draw in a certain color. And what color is that? It's the random color, which will load into the Y register. So we load Y with our random color value. So that's the whole of the draw routine. Hopefully that made sense. Hopefully that's also the most complicated thing we have to talk through. I should point out that these AceWin APIs, this isn't just for the VDC. This works on the 40 column display as well. So it'll work on, you know, VIC2 mode or C64 mode, whatever, as well as on the VDC display. But I can see there's a problem with the code that's going to potentially cause a crash if we did run this on the VIC2 or in the 40 column display. So I'm just going to put a directive here warning us, saying fix me for 40 column mode. And actually leave it as an exercise if you want to comment down below what you think the problem is with this draw routine that's going to not work so well if we try to run the program in 40 column mode. So warn just outputs some text to the console when you run the Acme assembler, so it won't prevent the program from assembling. We'll just get this text in the output. And that should be everything for our program. Let's briefly review. We've got our includes, we've got our boilerplate header, we've got our variables defined, our message, a main, a loop that actually loops, does our loop actually loop? Yeah, so as long as you don't press the stop key, it's going to continue looping until it gets to a count of 0. We set up our random number generator. We know how to get random numbers and scale them to the right values from using the SID, and we can draw. And based on the syntax highlighting, I don't see any syntax errors off the bat, but I won't rule it out. There could be some. But let's go ahead and save this. So we'll do Control K and X to save it and exit from Joe. And now we can use Acme to assemble our program. So we're going to do this with the Linux command because Acme runs under Linux. So we'll say Linux Acme, and we need to have a -i to tell it the path to find those include files. And from our dev directory where we're actually working here, we need to go up one level and then into idun-cartridge and then into the CBM subdirectory. And there we'll find all the include files that we need. And then we need to tell it the name of our source code, which is hello.asm. And that's all we need. Press return. You can see we get the warning about fix me for the 40 column mode. And it's done. It takes literally fractions of a second to assemble the program. And if we look at our directory now, you'll see we have this 134 byte binary for hello, which maybe it's worth pointing out. If you remember from part 1, the C code binary that we produced, excuse me, was about 3 kilobytes. So much, much bigger than this 134 byte assembly language version. Assembly language much more compact, especially for small programs, because you have to add in the overhead for C of the runtime library that you're accessing and the startup code, etc. And you don't have anything in your assembly language binary other than what we just typed in. That's all that's there. So it's tiny, 134 bytes. And if we run it, we get something very unusual. Not what we were expecting. So the reason we got gobbledygook, I believe, is because of this line right here. And this is supposed to be the length of our message string. And we got that by doing a simple computation where we took where the address where the message string starts and subtracted where it ends. But I did it backwards. it shouldn't be message minus main. It should rather be main minus message. That will give us the size. So I think what we were doing was we were overrunning our buffer and printing gobbledygook that was actually like code from our program instead of printing the actual message. So let's save this version. And let's run Acme again. And let's run hello again. There, that looks better. Except now, geez, it's ridiculously fast. Let's run it again. Wow. So that's 200 iterations and it's like 2 blinks of the eye. It's too fast. If you remember the C version, it ran considerably slower than that. Not unexpected. The 6502 in 2 megahertz mode is a faster CPU than the Z80 inside the C128. And, well, it's assembly language. It's small and tight. No C library calls. So yeah, no wonder it's faster, but we need to slow it down. So we need to add some kind of delay into our program. So how can we do that? Let's go back into the editor. And let's go up here and look at our loop. So in our loop, we would like to have some type of delay introduced so that it doesn't run quite so fast. Right now what we're doing is we're checking for the stop key, but that takes an instant, less than an instant. We need some more meaningful delay. There's lots of ways you could do delay in assembly code on the Commodore. You could, for instance, use one of the timers on the CIA chips. You could, for instance, use some interrupt, like from the VIC-2 blanking signal. What's it called? The scan line counter, basically, that the VIC-2 has. You could interrupt like once per frame on that and use that as a delay. You could just do a loop that does nothing, you know, or do nothing loop, or a loop within a loop that just wastes time by spinning in a loop for a delay. But rather than do any of those, because they're all kind of artificial, what I'm going to use is a toolbox API. So the toolbox is another piece of code that's included with the idun-cartridge, and it provides an API. It provides several features and APIs. One of them is for doing timeouts with callbacks. So just to make this a little more realistic, we'll use a timeout with a callback, because in a real program, while you're waiting for the timeout to end and the callback to be called, your program continues to run. So that the callback happens in an interrupt service routine, and meanwhile you can be doing other things like interacting with the user or drawing something on the screen. If you look at, for example, the SID play program that's included with the idun-cartridge, it uses the tool timeout API to play SID tunes. So let's see, in order to do that, we don't want necessarily a loop. We actually want like an update routine along with a loop. So we're going to have a loop that controls the timeout, and then we're going to have an update routine that's the thing that we call when the timeout expires. So let's define our update routine up here. So we'll say we'll have an update routine which calls getRan and draw and decrement counter, and let's not have it check for stop. Rather, let's have it increment a variable called wait for. So this is something that will tell us in the main loop that the update has completed. We'll use this wait for variable to know that the update's completed. So we decrement our counter, we increment wait for, and just to make sure our timeout is inactive, we'll call the cancel API. So tool timeout TMO cancel, and then we can return from our update routine. So basically the meat of the loop is now replaced with this update routine. So now up here in our loop, we can set up the timeout. So we're going to specify the address for our callback routine, which is called update. So we want the lower byte of that in A and the upper byte of that in Y. And we want our timeout time to be 1 GIF. So we're going to set X to 1. So that should be long enough, 1 Jiffy. And then we're going to call our timeout routine, which is tool timeout GIFs. There's also a tool timeout seconds. So your timeout can be theoretically anything from 1 GIF using this routine to 255 seconds using the seconds version of the timeout routine. And then this should be a good time to check for the stop key. So while we're waiting for our update to fire, we can do other stuff. So check for stop, and that's with the JSR ascon stop key routine. And let's just loop we're going to loop back to here. Why is it doing that? Unless you're pressing the stop key. So if the carry is set, that means the stop key is pressed and we should jump forward because we're going to exit the program. But otherwise, we should load A, the value of wait for, and if it's not 0, because it hasn't been incremented in the update loop, then we're going to continue to check the stop key. So basically, we're in a tight loop waiting on user input until the update happens. And if we fall through all of that, then we just want to jump up and repeat the loop again. So that's our loop and update. And now we no longer have this this version of checking for the stop key and exiting the shell. So we'll delete all that. And so now if we do press the stop key, you'll see it jumps forward to plus, which is basically going to do the same little exit, cancel the timeout and then RTS. So that will also send us back to the shell, exit the program. So yeah, it's a little clever there, maybe a little too clever, but the same ending for our update routine is also the ending for the whole program if we press the stop key. Otherwise, we're waiting on the loop and we circle back. So we need to initialize wait for. So let's make sure we do that. Let's do that here. So we'll decrement wait for. So we decrement it before we call the timeout routine, and then we increment it in the update routine. So it just jumps back and forth between 255 and 0. And of course we're going to need to initialize it to 0 to begin with. So up here at the top, we'll load a value of 0, and we'll store that into wait for. And then I think everything else is the same. And we just need to define wait for as a variable. So we'll make that another 0-page variable. And that can be in slot 5. So that's our new version of the program. That should run significantly slower. And let's save that. Exit, and we'll rebuild again. Value not defined, tool timeout GIFs and tool timeout cancel. Yes, so there's another include file that we need to include. for the toolbox. So we're going to source. This is going to be sys/toolhead asm. So that's our toolbox APIs are in that header file. So we'll save again and try again to build. And okay, now we just get our warning about the 40 column mode. And now if we run hello, yeah, runs much slower. So 200 iterations takes much longer. And we can also press the stop key at any moment to jump out of it early. So just like we wanted. Neat. So I hope this has been interesting and informative. I know it ran kind of long. I mean, assembly language is, well, it's wonderfully unforgiving. So it does take some time to craft working assembly language even for a simple program like this. But I hope you got to learn something about what it's like to program on a C128 with an idun cartridge and use some of the APIs. Of course, there's lots more source code available in the GitHub repository to learn from, assembly language source code predominantly. And we'll hopefully see you back here for the next tutorial, which will be writing this same program in Lua script and having it run on the ARM processor in the idun cartridge. Thanks for watching.